All right, we're doing the California Standards released questions in geometry now. And here's the first question, and it says, which of the following best describes deductive reasoning? And I'm not a huge fan of when they ask essentially definitional questions in math class, but we'll do it, and hopefully it'll help you understand what deductive reasoning is. Although I do think that you've probably deductive reasoning itself is probably more natural than the definition they'll give here. But actually, before I even look at the definitions, let me just tell you what it is, and then we can see which of these definitions matches it. Deductive reasoning is if I give you a bunch of statements, and then from those statements you deduce, or you come to some conclusions that you know must be true. Like if I said that, all boys are tall. If I told you all boys are tall, and if I told you that Bill is a boy, Bill is a boy. That's two separate words, and boy. So if you say, okay, if these two statements are true, what can you deduce? Well, I can say, well, Bill is a boy and all boys are tall, then Bill must be tall. You deduced this last statement from these two other statements that you knew are true, and this one has to be true if those two are true. So Bill must be tall. That is deductive reasoning. Deductive reasoning. Not must be tall, right? Not Bill must be deductive. So anyway, you have some statements and you deduce other statements that are actually must be true given those. And you often hear this, the opposite of it, not the opposite, but another type of reasoning is inductive reasoning. And that's when you're given a couple of examples and you generalize. If I said that, well, I don't want to get too complicated here because this is a question on deductive reasoning, but it's essentially, generalizations often aren't a good thing, but if you see a couple of examples and you see a pattern there, you can often extrapolate and get to a kind of a broader generalization. That's inductive reasoning, but that's not what they're asking us about this. But let's see if we could find the definition of deductive reasoning in the California Standards language. So use logic to draw conclusions based on accepted statements. Yeah, well, actually, that sounds about right. That's what we did here. We used logic to draw conclusions based on accepted statements, which were those two. So I'm going to go with A so far. Let's see. Accepting the meaning of a term without definition. Well, I don't even know how one can do that. How do you accept the meaning of something without it having being defined? Let's see. So it's not B. I don't think anything is really B. C, defining mathematical terms to correspond with physical objects. Well, no, that's not really anything related to deductive reasoning either. D, inferring a general truth by examining a number of specific examples. Well, this is more of what I had just talked about, inductive reasoning. So they want to know what deductive reasoning is, so I'm going to go with A. You use logic to draw conclusions based on accepted statements. Next problem. Okay, let me copy and paste the whole thing. This copy and paste is essential with these geometry problems. We'll have to redraw everything. Okay, in the diagram below, angle 1, and this right here, you should learn, means congruent. And when you say two congruents when you say two angles are congruent, so in this case they're saying angle 1 is congruent to angle 4, that means that they have the same angle measure. And the only difference why, there's a difference between congruent and being equal is that, congruent says, well, they can have the same angle measure, but they could be in different directions, and they can, the rays that come out from them could be of different lengths and all of that, although I'd often say that that's equal as well. But if we're dealing with congruency, that's what it means. It essentially just means the angle measures are equal. So we could draw that here. Angle 1 is congruent to angle 4, which just means that these angle measures are the same, whether we're measuring them in degrees or radians. All right, now what do they want us to come to conclusion? Which of the following conclusions does not have to be true? Does not have to be true. Not. Angles 3 and 4 are supplementary angles. So what does supplementary mean? That means that angle 3 plus angle 4 have to be equal to 180. This is the definition of a supplementary angle. Supplementary. I feel like I added a supplementary. Right, supplementary. So angles 3 and 4, they're actually opposite angles, and you could play with these. If you had these two lines and you kind of change the angle at which they intersect, you would see that angles 3 and 4 are actually going to be congruent angles. They're always going to be equal to each other in measure, right? So if they're equal to each other, and if angle 4 is, if let's say angle 4, we don't know what it is. If angle 4 is 95 degrees, then angle 3 is also going to be 95 degrees. If angle 4 was 30 degrees, angle 3 is also going to be 30 degrees. So I can think of a bunch of cases where this will not be equal to 180. The only way that this would be equal to 180, angle 3 plus angle 4, is if angle 4 were a 90-degree angle and angle 3 were also a 90-degree angle. But they don't tell us that. All they tell us is that angle 4 and angle 1 are the same, at least when you measure the angles. So I would already go with choice A. That does not have to be true. That will only be true if both of those angles are 90 degrees. Let's see. Line L is parallel to line M. Yeah, that's true. If that angle is equal to this angle, the best way to think about it is this angle is also equal to, and you could watch the videos on the angle game that I do. We do this quite a bit. But opposite angles are equal, and that should be intuitive to you at this point, because you can imagine that if these two lines, if I were to change the angle at which they cross, no matter what angle I do it at, that's always going to be equal to this. So angle 1 is going to be congruent to angle 2, and then if these two lines are parallel, if L and M are parallel, then 2 and 4 are going to be the same. Or you can think of it the other way. If 4 and 1 are the same, and 1 is the same as 2, then that means 4 is the same as 2. And if 4 and 2 are the same, then that means that these two lines are parallel. So this is definitely true. Angle 1 is congruent to angle 3. Angle 1, well, once again, if angle 1 is congruent to angle 4, right? So those two are congruent. And angle 3 is congruent to angle 4 because they're opposite angles. Or, instead of saying congruent, I could say equal. Then angle 3 is also going to be congruent. If this is equal to this and this is equal to this, then this is equal to that. All right. And then the last one, 2 is congruent to 3. 2 is congruent to 3. Well, by the same logic, if 1 is congruent to 4, and since 1 and 2 are opposites, it's also the same as 2. And 4 is because it's opposite of 3, it's congruent to that. All of these angles have to be the same thing, so 2 and 3 would also be congruent angles. So all of the other ones must be true, B, C, and D. So A is definitely our choice. Next problem. Let me copy and paste it. Okay. Consider the arguments below. Every multiple of 4 is even. 376 is a multiple of 4. Therefore, 376 is even. Fair enough? A number can be written as a repeating decimal if it is rational. Pi cannot be written as a repeating decimal. Therefore, pi is not rational. Which ones, if any, use deductive reasoning? Okay, so statement 1, every multiple of 4 is even. 376 is a multiple of 4, so this is deductive reasoning, right? Because you know that they say every multiple of 4 is even. So you pick any multiple of 4, it's going to be even. 376 is a multiple of 4, therefore it has to be even. So this is correct logic. So statement 1 is definitely deductive reasoning. Let's see, statement number 2. A number can be written as a repeating decimal if it is rational. So if you're rational, that means that you can write it as a repeating decimal. A repeating decimal. And that's like 0.333333, right? That's 1/3. That's all they mean by a repeating decimal. Right? But notice, this statement right here, a number can be written as a repeating decimal if it is rational. That doesn't say that a repeating decimal means that it's rational. It just means that a rational number can be written as a repeating decimal. This statement doesn't let us go the other way. It doesn't say that a repeating decimal can definitely be written as a rational number. It just says that if you are rational, if it is rational, a number can be written as a repeating decimal. Fair enough. And then it says pi cannot be written as a repeating decimal. Pi cannot be written as a repeating decimal. So, if pi cannot be written as a repeating decimal, can pi be rational? Well, if pi was rational, if pi was in this set, if pi were rational, then you could write it as a repeating decimal. But it says that you cannot write it as a repeating decimal. So therefore, pi cannot be rational, cannot be in the set of rationals. So therefore, this is also sound deductive reasoning. So both 1 and 2 use deductive reasoning, as far as I know. Let's see. Next problem. Oh, actually, I'm out of time. See you in the next